Good afternoon. My name is Addison Snell. I'm with Intersect 360 Research. We are analysts who cover the high-performance computing and hyperscale space, including topics like AI, which we've heard a little bit about at this conference today, cloud, big data, all of those span across into this space. I appreciate you letting me tag on to the end of the agenda today. I just arrived from San Francisco myself this morning, so I promise that my talk will be lively and quick, or else I might put myself to sleep. So I'll try to keep things moving. With regard to high-performance computing, I was recalling recently that I wrote an article in HPC Wire about 10 years ago. That was one of the earlier pieces I wrote for them. And it was entitled The New High-Performance Computing, the new HPC. And there was a lot that they were doing then around things like high-productivity computing, or how to capture things that went beyond these traditional supercomputing use cases. Now, I've got some traditional supercomputing applications up there. I cribbed all of these from the website of the Barcelona Supercomputer Center because I was just there recently for a Lenovo event 2 months ago, so it was in context of that. But what we were talking about then was going beyond some of these traditional modeling and simulation applications. And over the last decade, there was a big emphasis on looking at emerging commercial use cases for high-performance computing. And these are some that we've done case studies on over that time, starting with Simpson Strong-Tie, which is an American company based in California. I believe they sell their products worldwide. They're found in hardware stores. They make the brackets and joists and connectors that if you were building a house, they connect the pieces together so that your house doesn't fall down, particularly if there's some kind of a strong wind or shaking in the ground. And they specialize in being the high-quality component. They had just started using high-performance computing when I first talked to them several years ago, bringing in expertise from the car industry to look at how they could use modeling and simulation on some of their parts. To date, throughout my whole career as an analyst, this is still the only high-performance computing user I have ever met with where the primary material they are modeling most often is wood. And take a second and think about that as how complicated the model is, right? Wood is not simple. It's organic, it bends, it gets wet, it warps. There's all different kinds of wood, right? So this is not a cheap and easy thing. One of the first things they had to do was, like, they're calling the Army Corps of Engineers and saying, do you have any wood models that we can use? The second most common material they have to model is concrete, which is also not easy. It's not a homogeneous model. But to give you an idea of the kind of payoff they get, when they set up a stress test where they build something and they want to pull on it and see when does it break, what they have to do is build the thing, pour the concrete, check the calendar and say, great, let's meet back here in 2 months after the concrete cures, and then we can run our stress test. So this really sped up their ability to do testing, and then also what they hadn't predicted was it made them more responsive to contractors who were out in the field who would say things like, well, I have this building joist and I would like to drill a 2-inch hole in it as an electrical conduit. Is that okay? Will you still sign off on the structure? So now they could fire up their ANSYS model and look at it and say, well, maybe yes, maybe no, maybe can you put the hole 2 feet lower? Is that okay? Now you've got something where you can have a conversation about if you put the hole here instead of here, then yes, we'll sign off on the structure. So that was one right there. Another one that I found only recently, although it was a slightly older example, is this box of candy here that all of the millennials like to laugh at with the Tide Pods. Now, Procter & Gamble, under Tom Lang, became a well-known user of high-performance computing. And it was only as he was getting ready to retire, which I'm so sad about still, that I asked him, was there any product that P&G had wanted to come out with for a long time, but until they had modeling and simulation capabilities, they hadn't been able to do it cost effectively. And he had one like that, and it was this. It was Tide Pods. And he said it wasn't like we only just thought of that product. He said, we've wanted to come out with this for 75 years, right? The idea of having a single-use laundry thing. They said their competitors had come out with ones that were compressed powders. You could probably remember seeing those before. But while compressed powder tablets can work well in the dishwasher where there's hot water, they were never that satisfactory in the laundry where there's often cold water. They don't dissolve all the way, you get grit on your clothes. So he said they knew they wanted to come out with a liquid. Okay, fine, they have liquid detergent, they have liquid fabric softeners. The really hard thing to design, it turns out, is the envelope. And I hadn't spent any time thinking about it, but that envelope that encases the detergent, you're looking for a plastic that will dissolve immediately and completely in cold water, but not get dissolved by the liquid that's inside the envelope. And then it has to be shelf stable at a wide range of temperatures, humidities. You have to be able to ship it. Great. So you think you've got that. Now you have to be able to get the liquid inside the envelope on a manufacturing line at about 35 miles an hour, right? And get it into the box. And if you think you can do all that, the next criterion is if it costs more than about 25 cents per pod, forget it. No one's going to buy it. It has to be cheap, right? Because it's a consumer product. And it took a lot of modeling and simulation to do essentially what they do in biosciences, which is target reduction. They had lists of water-soluble macrochemicals that they could look at, but they had to get the targets down to where they could do practical testing and get this product on the shelf. And then people like me say, I thought of this 10 years ago. They should have done that, right? But it's a hard problem. And then the third one I put on here was this windshield wiper. I didn't name the company on this one. I don't have the permission for that, but I talked to the CEO of a company that makes windshield wiper blades, and they're aftermarket windshield wiper blades. And again, they consider themselves to be the quality leader in their segment. This isn't like the cheap windshield wiper blade. They want to be the good windshield wiper blade, right? And I asked him, did they ever do any modeling and simulation? I didn't know, right? And he said, funny you should ask, because they were just talking about that. The lead engineer for the new design that they were planning on coming out with had just raised the problem that he was concerned about whether they would have a problem with wind lift on the new design, which was a term I hadn't heard until that exact moment. But I could kind of get the idea that if you're out on the highway with all the wind, you can't have the wind pick up your windshield wiper blade off the windscreen, or else that doesn't work very well, right? It's got to stay down flat. It's an aerodynamic problem. And so he said, well, there's three things we could do. One is we could do a wind tunnel test, but we don't have a wind tunnel. NASA's not going to let us borrow their wind tunnel. Wind tunnel time is not cheap, so forget that. That's not going to happen. The second thing we could theoretically do is a computer simulation, but that's not an easy computer simulation, right? By the time you have not just the windshield wiper itself, but the car is moving and you have the wind or ice in the windshield wiper, so it's pretty complicated. You can do it, but it's not easy. And the third thing you can do is you can make the windshield wiper and put it on the car and drive it out on the highway and see what happens, right? So I thought he was going to say option 3, and I said, well, which did you do? He said, well, actually, we did option 2. We invested in high-performance computing to do the simulation. Really? Why? That sounds like it's going to cost more and take longer. Well, the engineer said that if we do that, that in the long run, we can do a better job of maintaining our quality lead over our competition, because we can do this kind of thing all the time. And that was what really started connecting all of these emerging commercial use cases of high-performance computing, was the people who would be the early adopters were the ones who viewed themselves as the quality leaders in their segment. If you had one question to ask a company to determine whether or not they were a potential adopter, the one question you want to ask is, who is the quality leader in your segment? Because every manufactured product has some metric of quality. It could be, a lot of different things. Who's the quality leader? If they say, well, that's us, then great. Now let's talk. How do you define quality? What does that look like? How can we help, right? And there are a lot of other reasonable ways to differentiate yourself, but it was the quality leaders who would go first. All right, so that was the new HPC that we've been talking about for a long time. In the decades since, we've had a lot of other things come up. We very quickly went into cloud as a major topic. There were a couple of years where if you went to ISC or supercomputing, it was just a cloud show, right? Then big data happened. And supercomputing very quickly became a big data show. That was all everyone wanted to talk about. And now we're on AI is the hot new thing. AI really represents a new category of applications within high-performance computing. And I really should have put just modeling and simulation over here. I liked how Stefan laid that out earlier with the different types of high-performance computing applications. Most of HPC's history, most scientific computing applications have essentially been deterministic, right? You plug in variables and you do X times Y plus Z equals whatever, right? You calculate an answer. There have also been certain categories of applications that are really more probabilistic. Rather than calculating an exact answer, you run it a bunch of times and see what happens. It's a Monte Carlo simulation. If I gave you the simple math question of if you shuffled 6 decks of cards together randomly and then peeled them out, what is the probability that you would have a string of 12 cards containing at least 10 spades? Well, you could try to do that math problem. It'd be a really gnarly math problem. Easier to just fire up the computer simulation, do it about 10 million times and see what happens and say, that's probably close enough. And there are a lot of Monte Carlo simulations in HPC. Now, AI is really a third kind of application that's not exactly probabilistic, it's experiential. I look at everything that's happened before and map that, and then I look at a new situation and I try to predict what this one looks like based on what's happened before. And we call it AI because that's basically modeled on how people learn, how humans learn, right? We see a bunch of previous situations, then we get something new and we do our best with the thing that's new. So we're training computers to work that way. And we're asked a lot about the AI opportunity, and I'd love to talk to you about that, right? The size of the AI market. In order to do that, I'm spending a lot of time on this slide, but I promise I have a point. In order to do that, I'm going to back up a little bit and talk about big data. Because that one we remember, right? I mean, it wasn't that long ago that we went through all of this big data enthusiasm, and people would ask us the same thing about the big data market. What's the size of the big data market? If you want to go into the analyst business and make a quick killing, right? You really want to rack up some dough really fast. Here is a simple 3-point plan for how to make a lot of money as an analyst very quickly. 1, describe a market that is very large and very fast growing. Make it as big and as fast growing as you want, no one will check, right? Big data is a $800 billion opportunity growing at 500% a year for the next 20 years. No one will check or ask you how you came up with that number because they want it to be big, because I want to justify my internal business investment. 2, in order to address that large, fast-growing market, all you need to do is one simple thing. And 3, that one simple thing is what you already thought it was, right? So if I had come out in 2014 with a market report that said our analyst view is that big data represents a $200 billion opportunity doubling every year, and all you need to do is Hadoop, we could name our price for that report and sell it all day long. The only problem with it really is that wouldn't make a lot of sense, right? It wasn't really true. And in fact, to name the big data market like as a distinct thing was in itself a bit of a misnomer, because what we found in our research was that big data didn't occupy a separate budget space. It wasn't a separate pocket of money that people had. Yes, people would say I'm spending money on analytics, but it was part of the enterprise budget they already maintained, right? They didn't have extra money flowing in from somewhere. And mostly it was data they already had, on storage they already had, with people they already had, and systems they already had. They probably got some new software, much of which was free. And if big data was really this $60 billion opportunity, or what people have said it was, well, where is it? Enterprise computing largely stayed flat over that time. Now, this is an illustrious point because if we had gone out and made a separate high-performance data and analytics number, which some analysts did, that would guide vendors to come out with things like big data appliances, or in some cases, whole separate big data business units focused on the big data opportunity, almost all of which would go on to fail, right? Because it wasn't a distinct pile of money. Now, fast forward to AI today, and that's exactly the point, is yes, it is a huge opportunity, just like analytics was, and analytics is still out there and it's still big, but the question is, where's the money? And is it new money, or is it old money? Or is it repurposed money, right? Where does it sit in the budget? Is it part of the HPC budget? Is it part of the enterprise budget? Or is it new budget? Is it a dedicated system, or is it a shared system? Is it the same configuration, or is it a new configuration? So we're trying to follow that all the way down to get a sense of where the big data opportunity is, or big data, the AI and machine learning opportunity is. Now here I'm talking mostly about the training, which is associated with high performance computing. There's certainly also a lot in the inference side, particularly in embedded and edge systems. We're not so much sizing that ourselves because we're looking for the things that have proximity to HPC and hyperscale. And hyperscale is really where most of the dedicated spending is right now. Now hyperscale we're talking about is separate from HPC. Here we're talking about the large web scale infrastructures at companies like Amazon or Google or LinkedIn or whoever. It doesn't have to be that big. It's got to be at least $1 million a year of spending on a web-facing, arbitrarily scalable application infrastructure, but that's our methodology around that. It is a very top-heavy market. In 2017, these are all 2017 year-end numbers because we haven't finished tallying up 2018 yet because we're still early in the year, and once we do, we'll probably go to our clients first before I give a general public presentation on it, but roll with me here for a minute. In 2017, there were 9 what we would call tier 1 companies that spent over $1 billion with a B on IT infrastructure for hyperscale in 2017. 3 of those spent over $2 billion. One of those spent over $4 billion, and quite a bit over 4, and might double that in 2018. It's going to be close. So there's a lot of spending out there. And when you look at that relative to the supercomputing market, well, a large supercomputer costs on the order of hundreds of millions of dollars. This is 10 times that spending every year. So when you see some of the vendors' attention getting drawn toward the hyperscale companies, that's why. You get a company like one of these tier 1 hyperscales, it's as if they're putting in 10 supercomputer class systems or more every single year. That market is now through its original major expansion. It is a little bit bigger than HPC as a whole, but is extremely top heavy into that top tier. Now, the reason that's important is because when we look at AI, deep learning, machine learning, in 2017, we counted about $4.5 billion on spending that was dedicated infrastructure specifically for machine learning, not shared infrastructure that also does other things, like I'm buying this just to do AI. But almost all of that gets consumed by hyperscale companies, right? You get the Googles and the Amazons and the Microsofts of the world. They will afford to have dedicated spending on AI. Within HPC, more than half of HPC organizations are running machine learning, but it was usually part of the same budget they already had, right? So now it's a question of how you're allocating budgets and how you're altering configurations. So when you ask me what's the size of the AI market, well, as a distinct market, it's that big and growing awfully fast, but predominantly in hyperscale. Within HPC, it is also pervasive, but usually not separate money. Everyone follow me on that? That's kind of an important point, right? Because when we size things, usually you're talking about revenue. Now, the exception to that within HPC is the biggest exception is in finance. For all the talk that you'll get about things like autonomous driving and personalized medicine, you're going to have personalized interest rates for all of you before you have personalized drugs for all of you, I promise. There's a lot of investment going on there, and the reason, again, is simple. There's a lot of money there. Finance is all about risk reward, and if they can individualize it, all the better. The hardest thing to get over in the finance world there is regulation. Because in many countries, if I individualize the pricing and then later someone comes back and says, you know, I've been watching because that's my job, and it turns out, do you know you've given white people 0.1% better interest rate than you've given Latino people, or you've given men 0.1% better interest rate than you've given women? Well, I didn't know that. My AI was doing it. Doesn't matter. The correlation is illegal regardless of the causality. And you're now an illegal jerk, and you can go to an actual jail with, you know, bars and guards and dogs and the whole thing. So the regulation is another thing to manage, but that's, you know, a huge linear algebra problem now on top of the machine learning problem, and it's something that they can try to solve. This is that use of machine learning at HPC sites. These are the people who are doing it already. These are the people who are, actually, these are out of order. This should be the second set of columns, and I didn't fix it. These are the ones who are working on implementing them within the next year. Then this second set of columns is now we're investigating. But the point is that it's over half already, and then, you know, most of the rest are already working on how to build machine learning into their environments. It's absolutely a huge trend. Mostly what's going on with that is you're changing configurations, and mostly what that means is GPUs or some other type of accelerator. Just like with big data, there was a change in configurations. The big thing that happened with big data was flash. People pulled a lot more flash into their environments, and storage got a little bit of a bump in terms of the overall budget mix, because even if I bought the same number of bytes, more of it was flash, that's more dollars per byte, and we saw a little bit of a bump in storage spending. Same thing is happening now with compute. There's more of the budgets getting consumed by the computational server portion, and most of that's because of the increase in accelerators. That's what this will look like in 2017 versus 2016. What looked like a relatively flat market at the top level was actually very dynamic underneath. Here's that bump that came in the server spending from more accelerators coming in. Storage was up a little, but the other soft areas, network, software, services, all declined, and cloud had a huge uptick, although from a smaller base. Cloud bashed through $1 billion of HPC and out into the rest. Now here, when I say cloud, I'm not talking about the hyperscale. What I mean here, this is an HPC slide. So this is HPC applications running in people's clouds. The money that an HPC using organization pays to Amazon or Azure or Google Cloud or whoever to run their HPC application. We do have a forecast now going into next year. Cloud should continue a big ascent, and early indications on 2018 was that it was pretty strong. Probably is going to beat our original forecast numbers, which are here. This looks like a pretty linear forecast. It's not really. But as far as really dramatic things happening in a forecast, my business partner, Chris Willard, who's our chief research officer, likes to say, when you do a forecast, it has to, in some sense, be bound by what's realistic, whereas reality has no such restrictions. Reality will go do whatever it wants. So as reality can be bumpy. Forecasts tend to be fairly smooth because we don't forecast things like floods and wars and other things that can be major disruptions in the market. Nevertheless, you can see this green cloud portion clearly has the largest growth rate. And everything in this, not just the different product and services categories, every vertical market, every tier from entry level up to supercomputer, every geography has its own growth rate. What you're looking at on this top level chart is the aggregate performance of the market. It is a healthy long-term market for the specific reason that we don't run out of science, right? I mean, the nature of high-performance computing is that it's tied to scientific computing, and until someday, I guess somebody could be at the last whiteboard with people cheering as they write out the last equation, and then great, science is done, we can go home. But mostly it's not like that, right? And even if you think of things that sound like they're done, my favorite example is in the year 2000, we mapped the human genome. It's like, great, you did it, we're done. Can we go home now? Well, no, what you really did is you just invented the field of genomics, right? Now there's way more work to do because you've achieved something, you've created a new field of study. The same thing will happen probably on the order of 10 years from now when we get it will be the first time a supercomputer has a comprehensive map of a human brain. That's going to be exciting, and it's going to sound like, great, we did it. But now we can use HPC modeling when that happens to do things like model what does Alzheimer's look like, or concussions, or autism. All these different things that it's tough to rip open actual living brains and look at, we'll be able to simulate. So that's why we believe in a long-term stable HPC market. As far as the new HPC goes, and things like cloud and big data and AI, yeah, they're new kinds of applications. So we kind of have this radical idea of, well, what could you call this new HPC that incorporates all of these things? I would propose that that term is something like high-performance computing, right? And if it's different than high-performance computing was before, well, yeah, that's what high-performance computing is like. It keeps changing because we keep discovering new things that we do. These are just some of the data segmentations we have under this, 2017 versus 2016. The growth was concentrated more toward the high end, and the lower growth was toward the low end. That should probably continue going into 2018. These are some of the server shares. HPE and Dell are the top two. They're a lot closer together than people realize, although HPE is still ahead. Cray had a down year, which does not concern me very much because Cray's business has always been inherently chunky and is sometimes up and sometimes down depending on large procurements. I was much more concerned about the down year that IBM had. That was a disappointment. They really should have, in my estimation, been doing better than that. One of the things we look at when we do this is a revenue chart, okay? This is dividing up revenue shares in the market, how much money got spent. One of the major inputs that we always have are the surveys that we do of the end user environment. People tell us what they have installed. This is what the surveys look like coming in. This will be similar to, but not identical to, our revenue model. This is an important input to our revenue model, but it's not slavishly followed because we also look at supply side and we do some modeling around the survey dynamics. Supermicro is kind of an outlier here because much of what Supermicro does is actually OEM'd through other people. And we try to assign the revenue to whoever was the last seller to the end user. So a lot of Supermicro's actual revenue gets embedded in other OEMs. AWS is the top named cloud vendor, by the way, out of all that growth. Here are the storage shares. Now, when you look at high performance storage or storage for HPC, a lot of the first names that you think of, like DDN and Panasys, actually don't have as much share as you would think. And that's because so much storage is out there that's just general enterprise storage in all of these commercial markets. I'm at an automotive manufacturer and I need storage, and well, what they do is they just give me a partition of the EMC or NetApp storage that we already have. It may not have been custom designed for HPC in the sense of HPC storage. It is nevertheless storage for my HPC application that gets paid for out of my HPC budget. And in fact, more of the revenue in 2017 went toward companies that also sell servers. A lot more of the storage got pulled along with the server sale in 2018. In 2017, I should say. This is what the site survey looks like behind the same thing. Now, here's where you get a big disconnect because DDN quickly goes to the top now. And DDN, I just said, didn't have as much revenue share. Well, that's specifically because of what I just said. When I buy DDN storage, I specifically think of it as HPC storage, and I have a lot greater likelihood of mentioning it in the survey as compared to if I have a NetApp partition or an EMC partition. I maybe don't think of it as much when I'm naming my HPC storage. So it's a bit of a sample bias in that case, but we have all of the other evidence that we need for putting together the other charts. It's worth saying, by the way, that on this Dell EMC storage, there's a lot of different products that can go in there. Just starting with plain old VMAX, which has nothing really to do with HPC at all, except there's so much of it out there. Some of it creeps into HPC just because my HPC budget pays for it. VNX, VNXE, the Unity brand now, does have specific HPC SKUs. They show up a little more often. Obviously, there's all of Isilon, but a bigger part of this you have to think of is Extreme IO. EMC sells an awful lot of flash, and that gets in here also. This is all types of storage. The different vertical markets, I don't want to read all of these all the way around, but the important thing is the commercial markets take up more than half of spending by revenue. It's easier to talk a lot of the time about the public sector research segments of the market, but commercial markets are larger and faster growing. All of the big growth drivers over the last several years have been in these commercial segments. Financial services we have is either the largest or second largest commercial vertical market, depending on your appetite for combining what's called large product manufacturing here, which is essentially automotive and aerospace, right? Cars, airplanes, tractors, and consumer product manufacturing, like the Procter & Gamble example I gave before. If you call those one manufacturing segment, then manufacturing's bigger. If you like to split them out and say large product is different from consumer product, then finance is the biggest. That's just a matter of taste. I show it here separate for the extra detail. Some of our clients like them together, some like them separately. I highlighted financial services to remind myself to talk about the AI, the machine learning is really most developed here compared to any of the other segments. Chemical engineering is on here, highlighted, because it's our highest growth rate in the forecast right now out of all of the commercial segments. When I say chemical here, I don't mean chemistry like biochemistry that's down in the biosciences, and there's even some petrochemistry in the energy area, but here I mean dedicated chemical engineering companies like Dow, DuPont, BASF, 3M, right? Those kinds of companies that do a lot of plastics and polymers. BASF just last year put in their first petaflop supercomputer, the Curiosity machine. We think that's going to get a lot of other attention through this space and drive a lot of the material sciences work to understand the nature of their chemicals, move away from wet bench and toward more modeling and simulation, like we saw happen in the pharmaceutical industry about 15 years ago. Just look for, as an example, at the Procter & Gamble example I gave at the beginning with the Tide Pods. Now you got Procter & Gamble designing their own water-soluble plastic. If I were at one of those companies saying, what, P&G is designing its own plastic now? Why didn't we design that and sell it to them, right? That's the kind of thing that should goose the chemical engineering industry into more high-performance computing usage. It's the fastest growth rate in our forecast right now. We do look at all kinds of other things like system interconnects. The interesting thing here is what's going on with OmniPath, which did get some very quick adoption, but then seems to be leveling out. It took most of its growth away, not from InfiniBand, but from high-end Ethernet. And that's going to be an interesting dynamic as it rolls forward to see what the future interplay of InfiniBand and OmniPath is. InfiniBand also shows up a lot of places, not just as a system interconnect, but Mellanox got a lot of its recent growth out of InfiniBand as a storage interconnect in high performance areas, and even appears a certain amount of time in HPC sites as a LAN. We track all the software, middleware areas. The big point of this slide isn't to show you what the top applications is, it's to show you how decentralized and disaggregated this market is. Another thing we tend to get asked as analysts a lot of the time is, what's the killer app, right? What's the one app I need to go do to dominate the space? And I try to say, well, HPC is not really like that. Okay, well, give me the 80-20 rule. What are the 5 apps I need to get 80% of the market? Well, no, still no, right? This is the top 10 get you to a third, right? And then it gets really small after that. And this is only looking at generally available applications. This already takes out all of the in-house application development, which there's a lot of in high-performance computing, but they all have n value of 1, right? Very few people use someone else's in-house developed application. So even this is after you take out all the in-house, which if you put them in, squishes the pie chart a lot more. So that's out of over 1,700 different mentions. A look ahead to 2019, which we've already started. I already mentioned early indicators suggest that there's strong growth in the market. I'm really looking forward to this notion of AI augmented HPC, and I think that is beginning to take shape now. This is not an either or kind of problem. This is a question of where does this style of programming or computing make sense versus other styles of programming or computing. I love the fact that it started the discussion of precision, right? Where do I really need double precision, 64-bit? Where can I do 32-bit single precision? Where can I do less? And that's not just for the machine learning part of the equation. I think there are a lot of areas in high performance computing where we've been doing relatively expensive 64-bit exact double precision calculations on models that aren't that good, right? And maybe it's better to save some of the computation and refine the model, right? And I think the notion of machine learning is going to help us come around on that, some kind of combination of where do you want to use machine learning approximations and where do you want to use double precision calculation. A couple of other great examples of AI augmented HPC, just that I'm looking forward to. In my career in HPC, we've heard a lot about things like person in the loop, engineer in the loop kind of simulations. In particular, as multi-physics was taking off like 15 years ago, the idea of having the engineer steer the model and do computational steering, then everything resolves as the engineer goes. Those are nice ideas, but they never really took off in great numbers, largely because the human latency is too slow, right, in terms of how it interacts with the model. But I submit that if we can teach AI to play Go or poker, we can probably teach AI to refine the airplane wing, right? Where we give it a set of parameters and the basic rules of the game and say, go try to do this. And it's not going to replace the engineer, okay? You still need the engineer. But the AI can sit there and play with a lot of permutations and then send you, here are 12 I'd like you to look at. The same idea of target reduction. Let's really look at, and maybe the AI thinks in a direction the human didn't think. We've seen that happen in some of the gaming applications before. So that's one. I'd like to see that. Another, on the storage side, we talked about data tiering, which is also on here. Storage tiers, I think, will continue to proliferate. Robert talked about that in his talk. We're going to have these tiers, and we're probably going to have more of them in the near term because of things that are in close, like NVDIMMs, which are kind of a hybrid between memory and storage. The big challenge with tiers is when to get your data on the hot tier, because as Robert pointed out, yeah, I really want everything in memory. I just can't afford that, right? So the economics drives having everything on the cold tier, and you get things like object storage, which are like valet parking, which would be great if the valet knew when I wanted my car and could have it there for me without me having to call and wait for it to show up. Well, so again, bring AI into this equation. What if the AI could get predictive about when I was about to ask for data, right? So that, it's monitoring what my data access patterns are, it's monitoring what I'm doing at the command line. If a storage operating environment can promote data onto hot storage before I ask for it, from whatever tier it used to be on, that becomes really high performance storage really fast, even if a lot of the data is in colder storage a lot of the time. And if you're going to roll your eyes at that, the hyperscale companies are doing this in different fashions. If I go onto Dan's Facebook page because I'm looking for pictures from a Halloween party 4 years ago, and I start scrolling back, and then you get that little wheel that goes because it's waiting to retrieve the data because it didn't know I was going to go ask. I'm not going to wait 7 seconds to get that picture because I'm a consumer. Consumers don't wait 7 seconds. When you're on your TV looking at movies, right, about which movie you're going to start, do you think they're waiting for you to select one before they start pre-buffering ones that you might pick, right? Same thing. If I select it, I want it to start. They can afford to promote the 10 things you're likeliest to pick, wait for you to pick one, and then put the rest back. If you finish watching this episode, they've already got the next episode getting ready to go, right? They can pre-buffer these things. That kind of thinking, I think, will start to permeate in the medium term into HPC. Now, on the hyperscale side, it's all about the battle to possess data. I want your data in my cloud. I want to own your data. Not own, I want to possess your data. I don't care who owns it. If I possess it, I win. That doesn't slow down. And I think we will see more acquisitions in this space. I think Azure in particular, with the acquisition of Cycle, might attract AWS or another cloud provider to do something similar with a service provider in that space. And I think middleware expertise becomes ever more critical against this backdrop of a lot of different technological choices, particularly in the processing arena, all the different storage options, and I'm trying to get it all to scale with different types of applications. So I think that's another area that this can go. Okay, thanks for having me in at the end of the day.